hello everyone, my name is Dimi. I'm a professor at HSSO, and this is joint work with former colleagues from EPFL, Bovel and Hamza, Remmal. So I'll be talking about generics. So to talk about generics, we need to have some generics. I will be using a lot of Scala to talk a little about this research, but this applies to your local friendly generic programming language. But here, let's look at this program. We have a trait, a shape here. You can think of it as an abstract class, if you will. And this has one requirement. I want to have an area method. And I have a function. Here I'm using Bovel polymorphism. So total area is a generic function. And I want S that is a subtype of the shape. And then I want to just take a collection of shapes and sum these areas. Right? It's very simple stuff. I'm sure everyone here understands what's going on. And we can write this kind of program in Java, in Python, in you name it. OK, so how can we apply this program? Well, we can do that. For instance, I'm creating a circle, and the circle is a shape. I'm implementing the area method. And then I'm applying the generic function. Now, when I apply a generic function, when I want to compile the generic function, there are two traditional approaches. There is the monomorphization approach. That is what your C++ compiler would do. The monomorphization approach consists of essentially rewriting your generic function by substituting the types with which it has been instantiated. So for instance, here, that would be the same as rewriting total area for an array sequence where I've fixed the circle type as being the shapes for which I want to compute areas. The other approach is erasure, and this is what is typically happening on the JVM. So in Scala, in Java, when we are compiling to a sort of type arrays representation of the objects, and now there is only one universal representation of your generic function, if you will, that is compiled and then executed by your machine. And it's up for engineering. There are pros and cons to both approaches. When we go through monomorphization, the cool part is that we get no runtime cost. It's as though you had written the function directly yourself. With no generics involved. It's also compatible with inline representation, so efficient representation of data structure. But I will come back to this point later. On the other hand, we get more code, right? Because every time I want to use my total area function with a different kind of shape, I need to rewrite the same function again and again and again. These are very, very similar piece of code, but it's a lot of code nonetheless. And also, I cannot have separate compilation. Every time I want to instantiate my total area function with a new type, I need to recompile it. I need to go all the way through optimizations and so on and so forth. And this is one of the big reasons why C++, for instance, is slow to compile. Now, if we go with erasure, we don't get these drawbacks. We have smaller code size because one compilation of the total area function is enough for all the possible shapes that you could imagine. I do have separate compilation. I can put that in a jar, and then I can reuse that jar for any other new subclass of the shape trait. But at the same time, I get the reverse from the monomorphizations, right? So I get runtime costs due to boxing my representation, and it's incompatible with inline representations. So what about these representations I keep mentioning? Well, on the JVM and in many reference-oriented languages, so your typical object-oriented programming language, if I do something like that, so this is the definition of circle. So circle is composed of an origin, which is a two-dimensional vector, and a radius, which is a double. And if I create an instance here of the circle, this is roughly what I get in memory. I get a first object that represents the circle here. It has a bunch of stuff, a mark, a pointer, a class pointer, and then finally I have some payload. And the origin is just a pointer to some other object that also has its own mark pointer, class pointer, and so on and so forth. So it's a lot of memory for just the actual bytes that I'm interested into. Well, actually, double is 8 bytes. Sorry for that. Let's pretend that I wrote float. So I really need only 12 bytes to represent my circle, but I have much more memory that is used here. And also I have all these indirections going on, right? I need to follow the pointers and so on and so forth. So in some applications, this is perfectly fine. In some other applications, maybe that are a bit more resourcing hungry, this is unacceptable, right? If you talk to designers of graphics engine, they will frown upon these kind of representations. So if we were to write that in C++ instead, we would get what I call an inline representation. So C++ is very proud of their zero-cost abstractions, which essentially is here represented by the fact that I can create a vector, a circle, put the vector in the circle, and I can do all sorts of wrapping. At the end of the day, I get my 12 bytes, or really 3 times 8 because it's a double. What's also nice about this inline representation is if I want to put my circle in an array of circles, then I need exactly that, right? It composed very well. As I said, you can wrap this into other objects or into arrays, and here I have only exactly the same sequence of bytes that I can put in contiguous memory. It will be very efficient if I want to do repeated access, for instance, in a loop, in a hot loop. So if I wanted to implement my total area function in C++, here is how I could do it. You could complain that I didn't use a smart type, but it's for the sake of making this representation simple. I have a pointer to an array of shape, which has this packed representation that I showed before, and I have a length, and then I can just run this loop. And well, if I go all the way down to the assembly code, then I get a bunch of stuff, but more importantly, I get that. This addition here is just computing the next index, and I just have to move a pointer into a large buffer. If I were to do that, were to look at what the Java code is doing, there will be a lot of indirections going on. So this is where the optimization penalty comes from the box representation. Okay, so this is about the representations. So now let's go back to the question of how we implement our generic function, and let's try to find another way to represent generics, one that is not based on subtyping. We will use type classes. It might be a bit scary. I'm sure the ICFP people here are very, very well aware of what type classes are, but for the other people, I will just do a very quick crash course. For ICFP people, it's the right time to check your emails. Okay, so we started with this code, right? We had the trait shape, and we used a bounded polymorphism to write our generic function. So the first thing we'll do is we will create another class here, well, a trait, and this is now parametric over this type self. Self will represent the type that are shapes. And the next thing I will do is that I will create the circle. The circle does no longer extend shape. Instead, I have this side function here that is creating what I call a shape witness. A shape witness is just an instance of shape for the circle. So basically, I'm just extracting the implementation of the area method in a different object, right? And the type system is not aware of this switcheroo. It's just me saying that the definition of the area method is somewhere else. Now, how can I apply this in a generic function? Well, I can create, it's a bit simpler function than the total area one, measure, that is just applying here the area of a shape. So it's a generic function, but it's no longer using bounded polymorphism. Instead, I'm just taking one generic parameter, and I'm taking two arguments. So one is the shape, and one is this additional side object that contains the method I'm interested in. And then I can just apply this method on the shape that I want. So this is nice and all. It re-implements the functionality that I had before, but this is a bit syntactically heavy. So let's see if I can use some sugars to make life look nicer. So the first thing I can do is to use context parameter or implicits. So instead of just a regular function, I will create a given function. This is essentially just introducing the instance in the implicit context. What it allows is that now the compiler can resolve on its own this shape witness parameter. I no longer have to write it down, so I can just remove it from my program, and it just disappears. And the next thing I can do is I can use this extension method in Scala, which is essentially another syntactic sugar trick that I can use to get back my nice dot syntax, dot-looking syntax. And the last syntactic trick I will use from the Scala tool belt is what we call a context bound, and now it looks almost exactly like the code that we would have written with bounded polymorphism. So I've done a lot of Scala tricks here, but I've done that to show you that type classes are really just reusing a concept that we already know. We just put the data on the side, and then we add parameters. And the syntactic tricks here, they can also be implemented in other programming languages, so it's not a Scala-specific thing. For instance, if I were to write the same program in Swift, it would look almost identical, right? So type classes is a sort of a general approach that we can use to implement generics. Now for the ICF people, I hope you finished reading your emails, because this is the part where we bring things back. Okay, so with type classes, another interesting thing is that we can show that the two techniques, the traditional techniques to completion that I showed before, can be represented using the type classes. So for instance, I can show static dispatch. Static dispatch is what C++ is doing. In C++, when we do the monomorphization, because we have substituted everything, the compiler knows everything. It knows the information of where we want to dispatch a particular method. So the RR method can be resolved statically at compile time. We don't need to go through a virtual table, no dynamic dispatch, and so on and so forth. And with the type class approach, we can do the same, because essentially what we can do is a partial application of the measure function, and the argument that was passed that represented the witness that circles our shape can be passed to the function directly. So we can do, with just partial application of the function, we can do static dispatch. So that gets us close to monomorphization. We can also show dynamic dispatch. So to get dynamic dispatch, what we can do is, in Swift, we can write this any shape. So shape is a type class, and writing any in front of it creates what Swift calls an existential container. An existential container is basically a pair that contains a witness that some type conforms to a type class, so an instance of that type class, and a value of the type being witnessed. So here, the any shape can contain a circle and a witness that circles are shapes. And now when I call s.area, I will do essentially dynamic dispatch, right? Because the witness can be understood as a sort of virtual table. It's just that I've expressed my virtual table directly within the programming language itself. So it's no longer a built-in thing that comes with object orientation. It's something that I constructed. And this gives me a lot of flexibility to play with these representations. Right, so this is an interesting here application of type classes. And if you're interested in existential containers, we presented a paper last year at MPLR explaining how this works in more details. I invite you to read it or ask questions at the end. Okay, so now we have monomorphization and we have dynamic dispatch or erasure through type classes, but can we do better than the existing approaches? And this is where existentialization comes. So existentialization is the process of trying to get kind of the both sides at once. We want to have the inline representations. We want to support separate compilation, but we need to have both of those things, right? So that was not possible with the erasure because we needed the box representation, and that was not possible with monomorphization because we couldn't get separate compilation. So what else can we do? Well, let's say that our shape type class that we had before, it had this generic parameter, right? So it was a shape of self, but now we create any shape. So this can be thought as a sort of erasure, right? I'm erasing the generic parameter of the shape. And then I have now my function area, which takes an any, right? This is also the erasure of the self parameter that we had before. But I know that my area returns a double. This doesn't change. the measure function that we had before, it also had a generic parameter that I need to erase. It gets replaced by any, and now I have this additional parameter, the W, which is the any shape. So it's the type class version approach that I had before, except that the context parameter, that was the type class instance, is now taking as an instance of this any shape trait that I have. And how do I implement now the body of the function? I just use my witness and I call the area method on it. It's basically exactly the code that we've seen before. Now what's interesting about this representation is that this is the only representation that you need to apply any instances of the measure function. I can use this measure function for the circles, for the rectangles, and for the triangles. It will not change the compilation of this specific method. So I have one on the separate compilation side. This one compilation result is enough for all the possible applications of shapes. Okay, so let's move to a more complicated example now to see if we solve our second goal. Our second goal was to support the inline representations. So this was our original motivation. We want this total area function that takes an arbitrary sequence. I don't know what kind of sequence I will use. It can be an array, can be a list, can be a tree, anything you like, and a shape that was subtype. So we know already how to replace the bound here on shape. We can use a type class instead of this subtyping relationship. But how can we deal with the sequence, right? Well, we create another type class, right? We can create a type class that represents sequences. So this type class here is a bit more complicated. It has two generic parameters, one for the thing that is a sequence, and one for the element that are contained in the sequence. And here, there would be many other things in a sequence type class, but for the sake of this example, I just used the fold left function. So let's assume our sequences just have this one fold left function, and fold left has this signature. It has one more generic parameter. This is the type of the accumulator, and then it's, I didn't write any implementation, but I'm sure everyone here understands how to implement fold left. Okay, and then this object sequence type of is some Scala salad that you don't need really to care about if you don't know Scala. It's just some syntactic sugar that I wanted to be able to write a nice definition of my total area function. So now total area function takes S, that is a shape. It uses a context bound. It's not a upper bound on shape. So I want an additional parameter witnessing the fact that S is a shape, and I do the same thing for T. So that means I want another parameter witnessing the fact that T is a sequence of specifically S. And then I can write fold left. So this is what I write in the user level, and this is as safe as we had before, but now just expressed with type classes. Why I wanted to use type classes here, because now I can run the process of doing existentialization on this particular piece of code. So what happens? First, the sequence type class definition becomes existentialized, so I just erase its parameter. So it becomes any sequence, and all the occurrences of generic type parameters become just any. So the fold left is a function that takes any. This is the sequence itself. The accumulator is also an any, and the function combining the elements with accumulator is an any to any, pair of any to any. Great. And now the total area is also existentialized. So we get x's. This is the any. So we want to the sequence on which we are the sequence of shapes that we want to compute the areas. And then we get two additional parameters which correspond to the context bound that we had before. So the fact that S is an any sequence, and the fact that T is an any sequence, and the fact that S is a shape. It returns a double as before, and what is the implementation? Well, it's basically doing dynamic dispatch, right? I just need to add this as instance of because I wrote that myself in Scala, but you can imagine that the compiler knows that these casts are fine, right? So here we are just recovering the information that the accumulator was doing additions on doubles. This we knew from the original definition. So what's interesting here is that now, again, this one compilation, this one version of the compiled function is enough to be applied to any sequence I want. Why? Because when I want to pass an array, I can definitely pass an array to an any, right? Any will accept anything. And how are we supposed to decode the array to compute the next element? Well, we just ask the AnySequence instance that tells me how to get to the next element of an array. What happens if I use a linked list or a tree? Well, same thing happens. I can pass my representations unchanged, and then I can use the instance of AnySequence here that is witnessing how to compute the next element. And, well, there is that. That's the existentialization. So there is much more in the paper, and that requires a bit more context to be set up. Was difficult to fit in just a single presentation, but as a teaser maybe of things that I didn't talk here, in the paper we explain how to do partial existentialization, because the nice thing is that this replacement of generic parameters for any, you can choose how much you want, how deep you want to run it. And that lets you do to combine monomorphization with erasure. So basically, you get a cursor that tells you how much you want to monomorphize your function. And so the trade-off between fast code, because there is some runtime here, runtime cost due to the casting, for instance, but you can decide how much of this runtime cost you want to pay for in exchange for having more code. I did not talk also about the way to allocate instances of existentialized type. So in these examples that we had, it was kind of convenient that all of the instances that we wanted to use were already in memory somewhere. But if you want to create new instances of your existential parameters, in the monomorphized world, it's very simple. In C++, for instance, you know exactly what is the size of a circle, but if it's existentialized, you might not know. And well, this is additional information that you need to carry through with your witnesses. And this is explained in the paper. Another thing that is also interesting with existentialization is that you get type reflection for free, because basically these witnesses, they explain what your type is, and so you can just consult the witnesses to ask various questions about the size of your type, the layout of your type, and this is how a programming language like Swift, for instance, implement their reflection. And finally, in the paper, we have a bunch of benchmarks showing that the overhead of existentialization is reasonable in languages like C++ and Swift that normally use aggressive monomorphization. So basically, we are paying for the additional cost of doing dynamic dispatch, and these costs are relatively well known, and there was nothing very surprising here. What was a bit more interesting is that if you try to apply existentialization on object-oriented languages like Scala, you get exactly the same performance, because in fact you just implemented virtual dispatch manually, and Hotspot doesn't care. And Hotspot optimizes it the same way. And well, if you want to learn more about that, you can read the paper or come to see our poster on Thursday, where me and my colleagues will be there to answer your questions if you have any. Thank you very much.
Thanks. I'm going to invite the next speaker to set up their slides while we take a question or two, please. Thank you.